Hey, Mr. Allred here. I'm going to briefly talk about Kepler's 3 laws of planetary motion, and then do an example from the book of one of them. But the first one here is that the orbit around the sun or a central body is an ellipse, and there's some formulas that go with that. There's a formula that, given the right information, helps you write an equation in polar form, which is what we've been talking about. So more or less all the first law says is that an object going around the sun forms the path of an ellipse, and we can write the equation for that. The second law here is kind of interesting, and there's formulas to prove it. But what we're going to say here is that over here on the left we are close to the sun, and we move faster when we're close to the sun, okay, because we have more gravitational pull, so more acceleration, so we move faster when we're closer to the sun. So we can move further along this ellipse in a set amount of time, and then when we're further away on the ellipse, we won't move as far in that amount of time. But what Kepler's second law says is that if we take the sector over here where we moved a long distance but we were close, the area contained in that sector is the same as the area contained in this sector when we didn't travel as far but we were further away. So more or less what he has down here is for the same amount of time, we may travel different distances, but the area of the arc or the sector we create would be the same. Okay, and we'll work with that. And the third one over here, his third law, says that there is a direct relationship between the time it takes to orbit and the length of the major axis, and the major axis is the long way of the ellipse. So we have the formula down here that kind of helps us track that. It has two things here. It has G and it has M. G is the gravitational constant, really small number here, and M is the mass of the sun for us, which is a really large number. What I didn't say here was A in this formula represents half that major axis, so we can still find the whole axis if we use that. So we're going to use this formula down here from the third law of motion to solve a problem, and then we will do some more in the coming days. So let me just set this up. So the question here is page 787, number 13. It says, estimate the length of the major axis of the Earth's orbit if the orbital period is 365.256 days. So let's kind of talk about what we have. We have the formula, which has the orbital period t, the length of the, half the length of the major axis a, G the gravitational constant, and M the mass of the sun. So 4 pi squared is a constant. So what we're trying to do is we're trying to look for the length of the major axis. So we're going to get that part by itself. So I'm going to get the a cubed by itself. Basically I brought it up to the other side and I manipulated everything. But I have my formula here. A cubed equals gravitational constant times the mass times the orbital period all over 4 pi squared. And I have all this information on the right, and I can drop it in. It does have some strange units that don't really line up right now. But a couple things to remember. One, we need to kind of get same units. So here I've got that a Newton is kilograms meters per second. So that's going to put the first one, if we change that over to kilograms, meters, seconds, meters, kilograms. So that's all going to help out. Ooh, I left something off the formula, very important. Didn't I? Yes. Hold on. Yes. So that was t squared over a cubed. So here I lost that. So let's see if we can get that in here while you're looking at it. So t squared, and t was the time in days. That should be squared. Okay, so we fixed that. So in the first one we named all the units. The second one, the m, the mass is in kilograms. The last one here, the time right now is in days. But if we rewrite newtons in terms of seconds, we need to change this 365 days over to seconds, which would be a really big number. But you're going to go through scientific notation, and what you're going to get here in the end, you'll get a number on the right hand side, and I think it'll be in terms of meters cubed, and then you can take the cube roots, so you'll get a equals about 15 times 10 to the 10 meters. And remember that a was half the major axis, and we're actually looking for the length of the major axis. So down here when we get to the end where we say double it, we will multiply that by 2. So the a is not our answer, but if we double that, we will get the answer we want. So if we multiply that by 2, it'll be about 30 times 10 to the 10 meters. Alright, so you can play with the units and work through that, but it does work out. Ooh, wrong button.